Thank you ever so much for the very nice introduction, Harold. So, yeah, as Harold says, I'm going to talk to you today about trusting quantum physics and how we can use quantum physics to transfer information securely. But before we start, or at least before we start properly, I'd like to do a little experiment with the audience. Are you a game audience? We'll find out. But essentially what I want to do is I want to demonstrate the importance of the problem that we're trying to solve here. And to do that, what I'd like to do is I'd like to transfer information from one person at one side of the audience to somebody at the other side of the audience securely among this crowded audience full of very dodgy people who would like to intercept this message. So I need a volunteer from somewhere over this side of the audience. And I should, brilliant. I should at this point out that there's a prize involved, okay? So what I'd like you to do is I'd like you to take this, don't show this to anybody else. This is obviously very secret and secure information. This is a Nectar card number, so it's not so important. But by writing messages on this piece of card here, I'd like you to transfer this number to the other side of the room, and the problem is you have to pass it to the people next to you along the chain and not let them know the same information. So you want to transfer the information. Let's have a volunteer over here, say. Volunteer? Perfect. So just put your hand up so she can see which direction you're going in. So you want to transfer the information to this gentleman and give the number to him, but to nobody else in the audience. And if you succeed, you get the chocolates, and if you fail, then everybody gets a chocolate, or until the box is empty. And we'll see how far we go. So this is the challenge, to send a message across a room to a stranger you've never met before without revealing any information to anybody else. Now this might seem like a very convoluted challenge. Why did I pick this challenge? And I picked this challenge because it's one that's fundamental to the way we live at the moment. So if you connect to the internet, for example, your personal computer is connected to a series of other computers, and from here you want to be able to conduct communication securely. So you want to be able to share secrets like your credit card information with people you consider important, like Amazon, for example, to get all your Christmas presents, and you don't want anybody else to read your credit card information. But the problem is you've never met with Amazon before, you don't know Amazon, you could be talking to anybody, so how can you possibly communicate your credit card information securely? Well, this young lady at the front, just pass it along. This young lady at the front is hopefully going to find a solution. There are existing solutions in mathematics. I have to point out your goal is to try and get the number, because if you get the number, you get a chocolate, okay? So you're not supposed to be helping. Okay. So we have this environment where we're sending secure information along a public network, and how can we possibly hope to do this? Just to illustrate that this is really a public network, I just did a trace route from my computer to one of Google's servers in this case, and you can see each one of these lines is a different computer. So my computer connected to 12 computers in between it and Google's server, which is this line at the bottom here. And so all the information that I'm transferring to Google could be read at any one of these 12 points in the network. But the problem isn't even that bad. Isn't even that nice, in fact. It's even worse than this, because in between these computers we have connections, and at any one of these connections somebody could be sitting and ciphering all the information which is being sent. So if I wanted to be really nasty, I could tap this line in front of Amazon here and record all the communications that are going into Amazon. And you might think that it's difficult to get information from a line these days, a transmission line, because nowadays we've moved from using electronic cables to transfer information to optical fibers. And I have a little demonstration here to show you just how easy it is to gain information from an optical fiber. So what I've done here is I've taken a green laser and I've coupled it to an optical fiber, and this is actually a standard telecoms optical fiber. So if you have fiber broadband at home, who has fiber broadband at home? Okay, you're very lucky people, it's brilliant. This is the kind of fiber which is delivering your internet connection, and to actually hack information from this fiber, to get the light out of this fiber at any other point but the start and the end, all you have to do is bend the fiber. So if I bend this fiber, you can see that light starts to leak out. And companies actually manufacture products which do exactly this. So they're designed specifically to tap information from optical fibers. I left my pointer over here. And the physics behind this is really rather straightforward. So the light's only being confined in the fiber here because of a physical effect known as total internal reflection. And this only works at very low angles. You can try this experiment next time you're in a swimming pool. If you put your head below the surface of the water in the swimming pool and you look along the surface, the water will actually look like a mirror and you can't see through the water. But if you move your head down a little bit lower at a larger angle, then you can see through the water. And that's exactly what goes on in this fiber here. As long as the light travels at very low angles, it's carried in the fiber. But as soon as we bend the fiber, the light starts to leak out the side. So it's actually really very straightforward to extract information from an optical fiber. So we have this problem where we have an open communication system and we want to be able to securely communicate with somebody we've never met before. So the question that my research at Lancaster University is trying to answer is, can we use quantum physics to provide a solution and to provide information security? And if we can, this is really nice because we trust physics, because we can prove the laws of physics. And so if you have to violate a law of physics to be able to break the security of a system, then you can probably not do any better than that. So before I show you how this works, I want to give you a little bit of a lesson on how light works. So you probably know light is a wave. Light is actually something called an electromagnetic wave. So you have an electric field component which oscillates, and you also have a magnetic field component which oscillates perpendicular to it. For the rest of the talk, we'll ignore the magnetic component because it's not so important. But light has a property called polarization. And if the electric field oscillates up and down along a single plane, then we call this kind of light polarized light, or in fact linearly polarized light. And we can define three different axes of linear polarization. So we can define a vertical polarized light, which is oscillating up and down in a vertical plane, or horizontally polarized light, which is oscillating backwards and forwards on a horizontal plane, or something that's halfway in between the two. We'll call that diagonally polarized light. Now, I hope you're relatively familiar with polarization because you almost certainly use it in various different ways in your life. The most famous example at the moment is in 3D cinema. So I hope you've all been to see a 3D film, hopefully here at the View Cinema. And 3D cinema uses polarization to deliver different signals to your two independent eyes so that they reconstruct a three-dimensional image. So what we have in a 3D cinema is we have two different projectors, one of which is horizontally polarized and one is which is vertically polarized. They each project an image on the screen, and then you sit in the cinema and you wear these glasses and they have filters in, and one filters out the horizontally polarized light and one filters out the vertically polarized light. So your glasses separate these two signals which are being sent to the screen, your eyes see different images, and that's how you get a 3D effect from the cinema. Now I should be, just to be completely honest and accurate here, this is how IMAX 3D cinema works. The actual cinema here in Lancaster uses circularly polarized light instead of linearly polarized light, but that's exactly the same effect, it's just a different form of polarization. Okay. So this is the effect that we know called polarization. The next question I want to ask is what happens when we try and measure the polarization of light, but not in quite the right basis. So now what I want to do is take diagonally polarized light, so this is light which is polarized at this 45-degree angle, and see what happens when it tries to pass through a vertically polarized filter. Now, if we try and pass horizontally polarized light through this filter, nothing would get through. And if we try and pass vertically polarized light through the filter, then everything would get through. So it makes sense that if we put something that's halfway in between, half of the light comes out the other side, and actually it comes out vertically polarized. And that's the case for classical light sources. So if I took my laser over there, that's actually linearly polarized. If I tried to pass that through a polarizer at 45 degrees, half of the light would go through, and it would be polarized at the same angle as the filter here. So that's essentially a very brief tour of polarization in classical light. But we can also think of the quantum properties of light. So if I take a light source and I filter it and filter it and filter it, and I attenuate it and I attenuate it and I attenuate it, as I reduce the intensity of light down and down and down, I get to a point where light will either pass through the filter or it won't. So I either get some light coming through the filter or nothing comes through. And if we take that light which comes through, we call that a single quanta of light, because it can't be split up any further, and it's a fundamental particle of light, and we call that a photon. And these photons have polarization in much the same way as my classical light source has polarization. And so we can do the same experiment with a single photon, which I picture as a particle here, as we would with our classical light source. And we can ask what happens when we try and put a diagonally polarized photon through our vertically polarized filter. And this is a really interesting question, because as I told you, we can't divide a single photon in half. It's a fundamental particle of light. So when it gets to this filter, half of it can't go through and half of it not go through, because we can't split it in two. And what actually happens is, half of the time its polarization changes and it passes through as if it was a vertically polarized photon, and half of the time its polarization changes to horizontally polarized and it doesn't pass through the filter at all. So if we average many events, half of the light has traveled through, but on each particular event its polarization is changed to either vertical or horizontal, and it either passes through the filter or it doesn't pass through the filter. And this is a really interesting property of quantum mechanics, because we've changed the polarization of this photon without knowing it. If we just looked at the results and we didn't know we were putting diagonally polarized photons through here, so if we didn't know this was diagonally polarized, in this case we would think that it was vertically polarized. We have no way of knowing that we've rotated the polarization of this photon. And this is a really spooky property of quantum mechanics. If we try and measure something in the wrong basis, we change the properties of the thing we're trying to measure, and we can't tell that we've changed it. And it's a really unusual property that has no analog with classical mechanics at all. In, I guess, the 1940s or so, this was summarized by a thought experiment in which physicists are very mean to a particular cat, which is put in a box, and it's put into one of these superposition states. It's put into a state which is collapsed upon measuring. And this is known as Schrodinger's cat, and you've probably come across Schrodinger's cat. I said this is very interesting, it's very useful. For security, it's phenomenally useful. If when we observe something, we change the thing we're observing, and we can detect those changes, then we can use the changes which are induced by observation to detect an eavesdropper on our line. So if we communicate with quantum states like this one here, which change when they're measured, and we can detect these changes, then if it's an eavesdropper making these changes, we can detect the presence of the eavesdropper. So we have at least now a seed of what becomes quantum communications, which is the field where we use basic features of quantum mechanics to detect the presence of an eavesdropper. So let me show you how that works in a little bit more detail. I'm going to change our network architecture a little bit. And now we have our consumer here, and she'd like to buy something from Amazon here, and I've connected them directly with a single optical fiber here. And unfortunately we have this nefarious chap on the line here, and he has a tactic. His tactic is to try and measure the signal which is being sent along this line, to copy it, and then to resend it, because it's no point being nefarious if your actions are going to get detected, because if you copy her credit card number, but she knows you're there, then she just goes ahead and changes her credit card number, right? You need to try and glean this information without being detected on the line. So this measure resend attack is a very common form of attack on such a system. But luckily our sender here is a very clever person, and instead of sending classical light pulses down this line, what she does is she sends single photons, and she randomly orientates the polarization of these photons. So she chooses them completely random, and she doesn't tell anybody which polarizations she's going to use. So now when these polarizations travel down, these photons with their random polarizations travel down this line here, our eavesdropper doesn't know which polarizations to measure. He has to guess, and sometimes he'll guess the wrong basis. Sometimes he'll try and measure, say, this diagonally polarized photon in the vertical basis, and he will rotate its polarization without knowing it. And then the field of quantum communications has come up with a protocol which can detect these unintentional rotations, and so we could detect the presence of this eavesdropper on the line. Now this process actually isn't used to exchange secure information. So our sender here isn't sending her credit card information at the moment. She's just sending random data. If these two decide that there wasn't an eavesdropper on the line, then they make a secure key. They make a secret out of this information here, and then they use that to encrypt their credit card information. So there's no loss of secret information if you do detect that an eavesdropper was on your line. So this is known as quantum key distribution, and you might not be convinced by all the quantum physics that I've told you so far. I talked very quickly, and it's somewhat complicated. But systems based on this principle have been available now for over 5 years, and there are several companies around the world which manufacture these systems. So in fact, I used to work for Toshiba in Cambridge making these boxes. They work very well. We can prove they're secure as much as we can prove the fundamental properties of quantum mechanics are valid. But the problem with current technology is that it's very big, it's very expensive, and it has other limitations. So this quantum key distribution system that I'm showing you here costs something like £100,000 to purchase. They're big 4U rack units, so they're this large. And they require a dedicated fiber linking the two systems, which is very, very expensive. So there are people who are willing to pay that much money for security. So military and large banks, people like this, they can afford quantum key distribution systems for security. But of course, the future is to try and make it affordable for everybody, so we don't have to use the internet insecurely. And so we have multiple research projects in my group at Lancaster working on various problems with quantum key distribution systems to make these systems practical, scalable, and to bring them to the masses. And I'm going to talk to you about one of these today. There are four main problems actually inside the quantum key distribution systems that we need to tackle. The first is that we need to be able to make these single photons. I haven't really talked about the single photons very much at the moment, apart from that you get them if you attenuate light enough. But it's actually very difficult to make a nice source of single photons, and we need to solve this problem. The second problem is that the receiver, we need to be able to detect single photons, and single photon detectors are very expensive. They need to be really, really sensitive, because photons are very difficult to measure. The third problem is that if we put single photons down a fiber, they can only travel about 100 kilometers before attenuation in the fiber absorbs the photons, and we don't have any signal out the other side. And of course, that's no good. And the fourth problem is that we need this dedicated fiber linking the two. It's very expensive to dig the country up and lay fibers between different points. It would be great if we could use the existing fiber architecture that we have for broadband communications. And of course, the fifth big problem is the size and power and cost of these systems. We really want to be able to miniaturize these systems so they fit on the end of a pinhead, so they're of the order of a micron in size. So we want to reduce the volume by a factor of 100,000 million or so, plus or minus. That's a big number. And we want to reduce the price by an order of 10,000 to 100,000. So it'd be great if we could make these systems and they only cost, say, £1 or £10 to make. So I'll show you how we're going to do this. These seem like very lofty goals, but actually, if you compare them to the advances that have been made in the semiconductor electronics industry, they're actually quite modest. If you look 50 years, 60 years back at the semiconductor world, a single transistor was of the order of centimeters cubed and cost an awful lot of money. And now transistors are of the order of tens of nanometers cubed, and they cost pennies for billions. So we have very similar scaling in numbers in the semiconductor electronics world. And what we're trying to do in my research group is to use semiconductor architecture, but instead of processing electrons now, we want to process photons. So we're using slightly different semiconductors. We're using optoelectronic semiconductors. So like the semiconductor that's in this laser pointer, this isn't silicon. This isn't the same semiconductor that you use for electronics. This is an optoelectronic semiconductor. But we want to build essentially circuits for light with our semiconductors. As I said, each one of these problems is a different research challenge that different people in my team at Lancaster are working on. I lied to you a little bit about this fourth problem. We've actually kind of already solved this fourth problem. So we did some very high-profile work a couple of years ago where we showed we could take a live broadband fiber connection and perform quantum key distribution at the same time. It's very tricky because the quantum signal is something like 10 to the 12 times weaker than the classical signal, so separating the two is very difficult, but we managed to solve this problem. And for the rest of the talk, I'll tell you about generating single photons and how we do this. But as I said, we have projects working on these two problems as well, and if you're interested in those, then please catch me at the bar later, and I'll talk to you about them. Okay, so single photon light sources. So how do we make a single photon light source? Well, a laser isn't a very good source of single photons. If I take a laser and I attenuate it down, and I attenuate it down, and I attenuate it down, even when you get to the single photon level, the probability that you'll get one photon in every pulse isn't 1. It turns out there's a random chance that you'll get no photons in a pulse for the same attenuation, and there's a chance that you'll get 2 or 3 or 4. And that's to do with the physics behind the way that a laser works. So they're not very good sources of single photons. But it turns out that single atoms are very good sources of single photons. And I can illustrate this process to you rather straightforwardly. So this is just a crude model of an atom. So we have a nucleus in the center here, and then we have an electron orbiting it. And these these circles here are meant to represent electron orbitals. So this is just a Bohr model of an atom. And here I've drawn the electron in the second shell here. So it's in the first excited state. Now, if we take an atom like this and we wait a while, then the electron will relax to the ground state and it will emit a photon. It will release the energy difference between these two levels as a photon. If this is a single atom, then if we want to get another photon at the same energy, we have to re-excite the atom again and wait for it to emit a photon again. And it's this time delay which means we'll always get single photons from this system. We can never excite it twice at the same time because this energy difference here is different from this energy difference here. And so we can never have two photons at the same energy at the same time being emitted by this atom. And this process has been known for a very long time. So Alan Aspect is a very famous physicist who worked on single photon emission. So we've known for a long time that single atoms are very good sources of single photons, but the problem is that single atoms are very difficult to tame. If I take a single atom, I need to make a big vacuum, I need to trap it in one particular place and keep it in the same place all the time. It's really not practical technology. And I told you we want to use semiconductor technology. So what we do is we use the semiconductor analog to single atoms, and this is an object called a quantum dot. Now we call it a quantum dot because it's a really small dot of one semiconductor which we embed inside another semiconductor. So this is an image here which was taken with an atomic force microscope, and for scale the size of this quantum dot here is 20 nanometers, so that's 20 times 10 to the minus 9 meters, so it's really a very small object indeed. And this is a picture from above of 20 different 15 different quantum dots. These are made of a semiconductor called gallium antimonide, and then the background semiconductor here is gallium arsenide. This is a cross-section through a quantum ring, so this is actually a quantum dot which has got the middle taken out, and it looks a little bit like a donut. And in this image here, you can see individual lines. These are planes of atoms, and this is a single atom here. These are single antimony atoms. So you can get an idea of the scale of these things. This is maybe 8 atoms high, and it's of the order of 100 atoms across, something like this. So there are of the order of 1,000 atoms in each of our quantum dots. So we're talking about large objects compared to single atoms, and they're very robust. We can put them inside standard semiconductor devices like an LED or like a laser and make them emit single photons, but they're still very small. Now, when these quantum dots confine electrons, the electrons inside the quantum dots, they have excited states in much the same way that atoms have excited states. And it's for this reason that we get single photon emission, just like we do from single atoms. So we have some very nice technology available to us at the university. And we actually make these quantum dots actually at the university themselves. And we use a big machine. This is called a molecular beam epitaxy reactor. And for scale, I suppose this is the size of a small car, something like this. Inside here, we have very little indeed. So inside this machine, there is a vacuum, which is almost perfect. So we have a vacuum inside there that's better than most of space. It's 10 to the minus 10 millibar on a very good day. Is it a very good day today, Mike? Is it 10 to the minus? You don't know. You've not looked. Okay. Sorry, there's an MBE grower on the front here. So essentially what we do inside this machine is we build our semiconductors one layer of atoms at a time. So I told you each one of these is a layer of atoms. As we grow this and we build this structure up inside the MBE machine, we can choose which material we want to put in each one of these layers. And if we have any impurities, if we have any air in this machine or any random materials, then they get incorporated in these atomic layers, and we don't want that. We want to control with atomic precision the materials that we grow. So that's why we start with such a good vacuum. And this looks really complicated and crazy. It's actually relatively simple. Almost everything you can see is a vacuum technology to try and make the vacuum inside there as good as possible. And the machine itself is really very simple indeed. If we look inside the machine, we have this big open space here, which is our vacuum. We have a target here, which is where we grow these semiconductors. And then we have these chambers at the bottom here. They're full of liquid metals from groups 3 and 5 of the periodic table, and we'll use those to make our semiconductors. Now, one of the most famous semiconductors is gallium arsenide, and I've drawn this in blue and red down here. So blue are gallium atoms and red are arsenic atoms. If we want to grow gallium arsenide in this machine, all we do is we open up a cell here which has molten gallium in it, and a cell here which has arsenic in it, which sublimes, so it's actually a solid here. We just open and close shutters in front of these to expose this target area here to gallium arsenide. And if we get the temperatures of these correct, then we'll grow a very nice crystal of gallium arsenide. If we want to switch to growing a different material, so here we're switching from gallium atoms to aluminium atoms, all we do is we close a shutter which is in front of the gallium cell here, and we open a shutter in front of the aluminium cell. So it's really very straightforward to switch between growing one material to another with atomic precision. Now these two materials in particular are very useful for making laser structures, so all the red lasers, things like this, and infrared lasers in CD players, they're all gallium arsenide based. This is just a real world demonstration, so obviously this is a stick model that I put together. This is an actual sample which represents the picture that I showed you previously. This is the bottom of the sample, and we're growing in this direction here. Each one of these layers, the black is gallium arsenide, the white is aluminium arsenide, and you can see I've changed the layer thickness and the number of layers in each one of these stripes. If we zoom in, so this is a transmission electron microscope image, you can actually get atomic precision, and you can see the change here from aluminium arsenide to gallium arsenide, and you can see the individual dots of atoms there. You can see that the transition from growing one material to the other, it has almost atomic precision. So there's a little bit of waviness around the lines, but we have very, very good control over the materials that we grow in this machine. Now, you can see that what we've done here is we've grown, this is a cross-section through a slice through the center of the wafer that we've grown, and we've grown essentially two-dimensional layers. We've grown big sheets of aluminium arsenide sandwiched between layers of gallium arsenide. And what I told you we wanted is three-dimensional structures. So we want these quantum dots. They're little tiny blobs. They're not two-dimensional layers. And there's a little trick we can use to grow quantum dots rather than quantum wells. And that is to try and put one material on top of another where the two materials are not compatible. So instead of putting aluminium arsenide on gallium arsenide, now we're going to try and put gallium antimonide on gallium arsenide. And it turns out that the atoms in gallium antimonide, they want to stay further apart than the atoms in gallium arsenide. So when we put gallium antimonide on top of gallium arsenide, strain builds up very, very quickly. So when we put the first layer on, it sits nicely, but it's not very happy. And then 2 layers, it's really not very happy. And after 2 layers, quantum dots form naturally. And this is much like putting water on a glass surface, where the surface tension causes the water to bunch up and form droplets. almost exactly the same process here. The strain is causing our gallium antimonide that we've put down to bunch up, and this happens on the scale of 20 nanometers or so laterally, and we form these quantum dots that we need. Okay, so just a look at a few more pictures. Everything I've shown you in cross section at the moment. The position that we actually make this cut in cross section is random, and so when we take a cross section, say through one of these donut structures, sometimes we cleave through the side and we see an image like this, and sometimes we cleave through the middle and we see an image like this. Now you might wonder why we get donuts sometimes and sometimes why we get quantum dots. We understand the reason why. It's to do with very complicated dynamics during the growth, and I can talk to you about the reason for this. But it's actually really nice. These quantum rings we've shown, these donut structures we've shown, have much better optical properties than a standard quantum dot. And this material combination, this gallium antimonide with gallium arsenide, works really, really nicely above room temperature. So this is the first time anywhere in the world where we've had a semiconductor nanostructure system like this, which could emit single photons at room temperature, which is obviously very important. If we have to operate at low temperature, then these devices aren't very practical. And so it was really a big goal for many years to be able to make these things operate at room temperature. So this is very nice. These are really nice nanostructures that are only made here in Lancaster. Now, when we make some of these quantum dots, we actually end up making a lot of them at the same time. So we grow on wafers which are, take this off, are 2 inches in diameter. So they look like this. If you can pass this round, please don't touch the surface. But you'll see if you have a good look at it, it's an almost perfect mirror, and that's because it's atomically flat on the surface. Once we finish growing, we have something like 10 to the 12, so a million quantum dots on the surface of this sample. And if we want to take each one of these quantum dots and make it into an LED structure, we have to dice this wafer up into 10 to the 12 individual little pieces and make them into LEDs. And we have another very nice facility in Lancaster to do this. We have a brand new quantum technology center. And this is a clean room. So you can imagine each one of these pieces is very small, and the processing that goes into making LED structures is rather difficult. We're looking at an object which is 20 nanometers across, and if a speck of dust lands on this object, then it ruins that device. So we have to work in a very, very clean environment. And in this clean room in the bottom here, we have an environment where we have fewer than 100 particles per meter cubed, so fewer than 100 specks of dust per meter cubed when we're making these devices. Now the actual structures that we make, you wouldn't think look any different from the LEDs that you can buy. So you've probably seen large LEDs like this. If you look inside an LED like this, all you have is you have a dot of semiconductor like the ones that that are being passed around. And that's just inside a structure that allows you to apply a current, and it has a lens attached to the top so we can get the light out efficiently. The structures we make are exactly the same. We're just changing this little dot of semiconductor for one that has a quantum dot in the middle. So when we apply a current along these leads here, we get single photons instead of classical light. Okay, so we've made our single photon LED. Now we want to prove it, right? We want to prove that we have single photons. How do we actually do this? Well, it's actually really straightforward. I told you that we can't divide photons in two. So all we do is we take our single photon LED, we take the light from it, and we try and divide it into two. So we pass it into something called a beam splitter, which is a semi-silvered mirror, and all it does is it tries to divide the light into two different paths. So half the light goes down this way, and half the light carries on this way. And if we truly have single photons, then the photon will either go this way or it will go this way, but it can never go both ways at the same time. So we can never have a signal on both of these two detectors at the same time. So we do this experiment, and we get a graph that looks like this. And this is dual coincidences with these two detectors. And this is when there's zero time delay between the two detectors. And you can see this really nice dip here. This indicates that there's almost no events where we get a photon at the same time on both detectors. So this proves we really have the single photons that we were after. Now, you can see there's a very small bar at the bottom here, and this is because these detectors are actually not very good. So there's a slight dark count. We get some counts when there's no light coming into these detectors, and so we always get some background signal, and that's why we have this very small bar here. But we have a source of effectively perfect single photons now, which is very nice indeed, and it works at room temperature, and it's a standard semiconductor architecture, so we can mass manufacture these devices for the first time, which is very good. So that's the results. This is the lab. I'm an experimentalist, so I always like to show people pictures of the lab. This is two of my students, Chris and Johnny. And here they're looking at quantum dots which are mounted in a cryostat. So I said they operate at room temperature. They do, but we typically cool them down. The physics gets simpler and the experiment gets a little bit easier at low temperature. So certainly when we're prototyping or just studying the physics of these things, we work at low temperature. And then you can see there's a complicated array of optics here guiding the light from these quantum dots into a spectrometer, which is just off the picture here. And that's where we do these single photon measurements. So as I said earlier, the single photon project is just the first step, and there are 4 other projects which are ongoing at the same time. The final device will actually entail incorporating a second element which will allow us to modulate the light. So we need to rotate the polarization of our photons randomly for these quantum key distribution systems, and then we need to couple them into a fiber very effectively. So we need to also incorporate some optics to couple them into a fiber. The final sender device will probably look something like this, or at least that's what I've promised. This is of the order of a few microns cube. So we should hopefully be able to replace these very large sender units, which cost 50 to 100,000 pounds each, with these really small specks of semiconductor, which cost pennies each. Of course, there's a receiver element as well, which needs to be developed completely independently, which sees, instead of having a quantum light source here, we have a detector here, and we have something to demodulate the information. But effectively, we should be about 2 years away from mass manufacturing these components. Okay, so I want to, before we get to the end of the talk, I want to come back to our problem. How did we do? If you got my super secret Nectar card number, did anybody else manage to read it on the way? Oh, you did? Oh, I'm sorry. Okay, so that means everybody gets a chocolate, so that's very good. So yeah, please come and get a chocolate afterwards. There is actually a solution to this problem which is used today. Obviously, when you purchase something on Amazon, you can be fairly secure in your purchase, though you certainly shouldn't be 100% secure. We use things called public key cryptography algorithms to perform an operation like this. And the first proposed system, which is really elegant, is known as the Diffie-Hellman protocol. And what you'd have done is you two would both have made public keys which you'd have shared first, and then you'd have encrypted your, or I should say my Nectar card number using these public keys. If you're interested in maths, I really recommend looking up the Diffie-Hellman Wikipedia page. It's a really, really interesting protocol, and I can explain it to you afterwards, but it would be a seminar on its own to explain to you exactly how it works. But it's really very elegant. The biggest problem is that we can't prove that this is actually secure. And in fact, we can prove that it's not particularly secure. There have been many high-profile attacks against systems like this in recent years. And just last year, it was revealed that the NSA have a big facility where they essentially spend an awful lot of time on supercomputers cracking codes like this. So we do need secure solutions to replace these systems. Okay, so just to summarize, I hope I've convinced you that communicating securely in public is both difficult but also really important, and we can achieve it with quantum physics. And at Lancaster University, we're making compact semiconductor systems which will hopefully solve these problems, but also solve them with really good size, weight, and cost metrics, so we can actually afford to bring this technology to the mass market and not just big, rich banks. And I should also thank the other people who work with me at Lancaster University. So this is my research team. These are my 4 PhD students. And then I collaborate with the computer science department. So these are 3 researchers in the computer science department. Thank you very much for your attention.